All right, here we go. So, review from yesterday. So you have air, light's going from air to water. Think, don't talk. What's going to happen when the light goes from air into water? Think without your words. It will do what? Bend towards the normal line. Okay. So, by comparison, if you're going from water into air, it will bend away from the normal line. Good with that? Follow-up question. What will happen if I increase the angle of incidence? I think I'd do A, B, or C. A, B, or C. It's going to bend more away than the red. Does that make sense? Okay. Will this process go forever, or is there a certain limit? At some point, what happens to the refracted ray? At some point, this refracted ray goes parallel to the surface. You okay with that? Okay. This angle there is your critical angle. Okay. If theta 1 equals the critical angle, then the refracted ray goes parallel to the surface. Making theta 2 equal to what? Tell your neighbor. What would be the value of theta 2? What do we always measure the angle from? From the normal line. So theta 2 is going to be equal to 90 degrees. Everybody see that? Measuring from the normal line. Okay. Okay. It's critical angle. All right. So all right, for this half, so here, as the light goes out of the water into the air, it creates, it refracts and bends away from the normal line. Good with that? As we increase theta 1, the angle of refraction is getting more and more as well. But then at some point, that refracted ray goes parallel to the surface. Okay, right there. I don't know if you can see that on the wall. Okay, and then if we go beyond that, okay, before I go beyond that, notice we have one ray. Where did you go? One ray that is refracted, another ray that's reflected. See that? Okay. Now, here's a critical angle. Watch what happens to the reflected ray when I go beyond the critical angle, past the critical angle. See how it gets brighter? The reason for that is because none of the light is escaping out of the water. Once you reach the critical angle, if you go beyond that, none of it gets out. All of it's reflected. This is known as total internal reflection. Cool with that? So we're going out, boom. See how it got brighter? Okay. Where you all? Okay. It's refracted, bending away from the normal line. Here we're getting close to the critical angle. And then going beyond that, boom. See how the reflected ray gets brighter? So getting out, boom. See how it gets brighter? Good there? Jesse? Good question. Okay, a lot going on here. We'll just eliminate, let's see, get 3 dots. Where was 3 dots going? Right there. Okay, so this is a reflection off the glass window of the aquarium. This is coming refracting. Then another one is bouncing around, reflecting, and then getting out there, like it's refracting from here. And then another one may or may not bounce. Cool with that? Good question. All right, here come the lights. All right, so when light goes, some of it gets out, some of it reflects back in and obeys the law of reflection. Okay. The blue, same thing. Some of it gets out, refracted, and obeys the law of reflection. The green is at the critical angle. Some sort of gets out, and some obeys the law of reflection. But if you exceed or go past the critical angle, so we're beyond the critical angle, none of it gets out, and all of it obeys the law of reflection. This is known as total internal reflection. Total internal reflection occurs when theta 1 is greater than your critical angle. Total internal reflection occurs when theta 1, your angle of incidence, is greater than your critical angle. Does that make sense with what you observed? Okay. To make a comparison, though, here we have water to air. What about from air to water? So that's going to bend still towards the normal line, just not as much. Okay with that? Everybody have a guess in their brain what this is going to do? Still bends towards the normal line, just not as much as what is going on down here. Is it possible to have a critical angle going from air to water, going from a low index of refraction to a high index of refraction? No, because we're always bending towards the normal line. Only get a critical angle when you bend away from the normal line. Does that make sense? Okay. So Two requirements, two conditions for total internal reflection to occur. Number one, theta 1 must exceed the critical angle. Number two, light must go from a high index of refraction to a low index of refraction. It must bend away from the normal line. Has to go from slow to fast. Must go from a high index of refraction to a low index of refraction. Good with that? And that's what the pre-quiz was going to cover. See what I could do in pre-quizzes? Factoids are kind of like, feels like I'm lecturing. Okay. We're ready for the application. Talk to your neighbor. Correct answer is? Correct answer is E. Good to that. Okay, you only get a critical angle when going from low to high. This does not produce a critical angle. Good there? Okay, all right. If I ask you to calculate the critical angle, I do not need to tell you which one is N1 and which one is N2. Okay? I need you to think which one's N1, which one's N2. Tell your neighbor. N1 is what? Which one's N1? Glass, N1. It has a higher index of refraction. This is N2. Okay. So, using Snell's law, okay, N1 is 1.52. Sine, I'm leaving a blank, 1.33. Sine, I'm leaving a blank. Okay. Theta 1 and theta 2, one of those, you know the value. Figure out which one you know and what is that value. In your brain, ready, set, talk. What?
No, we're actually doing a lot right now.
Say it again.
The last thing is
Oh, good question. Great question. Okay, what angle do you know? Theta 1 or theta 2? Theta 2, what is the value of theta 2? 90. Because it makes the refracted ray go parallel to the surface. So, theta 1, that is your critical angle. That's what you're looking for. Okay? Good with that? Flipping those two is a very popular mistake. Okay? So, pre-cal folk, sine of 90 is equal to what? So I get 1.33 divided by 1.52. You get 0.875. So I've done this a couple times today. Inverse sine, 61 degrees. This is kind of nice because it's a user-friendly equation. If you screw this up, if you mix and match this, you will be finding the inverse sine of something greater than 1, which your calculator will readily tell you, error. Go ahead and try it again. But at some point, go, maybe the calculator is trying to tell me something. Try something different. You can mess that up. Good with that? Okay. So this is just in picture form what I showed you in the fish tank. So the critical angle, we'll say, is 61 degrees. Some of that's reflected, some of that's refracted. Parallel. Here's your theta 2. That makes sense why theta 2 is equal to 90. Okay. If we go beyond that, if we exceed 61 degrees, let's say this is 62 degrees, none of the light gets out. It's all reflected back in. Total internal reflection. Good with that? Okay. Saw that already. I just made this. I just made that. You don't have it.
These ones are just. I don't want it to make it a crumb. We're still on that one again.
Want some duct tape?
Duct tape, nah, I'm good. Oh my gosh.
Tell your neighbor.
How can I have a needle and thread?
Sorry. Got thread.
I feel like you would though.
I don't have a sewing needle. I got it.
Do you knit?
No.
I wish that hobbies. Like you knit or you sew. What are your hobbies outside of this? Curious. What do you do?
I like to play stuff.
You like what?
Play stuff outside.
Play stuff outside. What does that entail?
Like being outside, like hiking.
Okay, being outside. You said
like,
playing stuff outside.
Like,
what does that mean? Like
soccer, ultimate frisbee. Yeah. Campfires, not knitting by the campfire.
So do you crochet?
I don't, sadly. I could sew something up.
Sew something up.
I mean, it wouldn't look pretty, but if there's a hole, I'd probably close that up. Tell your neighbor the answer to this question. No way.
No way.
No. You got distracted.
Sorry, my sweatshirt just rip that I got. I grabbed it.
Oh, I know.
I don't know. I'm gonna go outside my weight locker to get my t-shirt out of there.
Correct answer is? I got an A, B on the table.
I don't know. It's just
Okay. Orange is gonna make it out. Green, gonna make it out. Blue, not gonna make it out. Purple, Not going to make it out. A and B. Okay, will be totally internally reflected. You're right. That's all I got. I'm limited in my marker supply here.
Mix your yellow and red. Wait, if you would have yellow, then he would have done that.
Yeah. All right. Try this one out.
Is this also?
Thumbs up when you have a guess. Have a conversation.
So one of us or one of us could be C probably. Curveball. None of those answers are there.
What do you say? Correct answer is? Man, didn't work. Correct answer is A. All right. Here's what I was trying to lead you to with the last question. Let's say this is 30 degrees. Okay. If I come in at 20 degrees, some of it gets out. Some of it's reflected back in. Okay. If I come in at, so that's 30. If I come in at 40 degrees, that exceeds the critical angle. That goes beyond 30. It's all reflected back in. Totally internally reflected. If I go to 50 degrees, totally internally reflected. If I go to 70 degrees, totally internally reflected. Okay. Over here, that's 60. The critical angle is 60 degrees. So 20 makes it out. Some's reflected. Blue. 40 degrees makes it out, but some's reflected. 50 degrees makes it out, some's reflected. Only 70 degrees is totally internally reflected. See how lower critical angle causes total internal reflection to happen more readily? Does that make sense? Good at that? Okay. So, what? No? So, what scenario is going to cause that? without doing math. Check that out. Look at the picture. You know the answer to that. But look at the overall picture of A compared to B. What's going to cause that? Have a conversation. Correct answer is D, dangerous dinosaurs. You want the biggest contrast in indices of refraction, the biggest change in speed. Here, this is difference of 0.3. This is 0.2. This is 0.5. This is 0.9. You want a greater bend. Light bent more here than here. Okay. So, see how diamond has an index of refraction of 2.4? I mean, that's crazy. That means light's going really slow through a diamond. This is why diamonds look so cool. Okay? They are cut in such a way that light, a lot of light, is totally internally reflected on the backside of the diamond. And it's only allowed to come out on the top. Okay? So if you look at an engagement ring, it's usually elevated and the backside is exposed, meaning that light can come in from all directions. But light that comes in is cut in such a way that a lot of, like, it's a small critical angle, so a lot of that light is totally internally reflected on the back, and it's only allowed to escape out of the top. So that's why a diamond looks so brilliant when you look at the top of it. Does that make sense? Now, you can mess that up if you cut it wrong, but most of the times when you buy a diamond in the store, they're cut well. If you're going to pay thousands of dollars, someone has evaluated that. Okay. Cool that. So if you look at the backside of a diamond, it won't look black. It'll look, but dull. It won't, not as brilliant as the top, because some light does get escapes, but not a lot. Okay. Another application to total internal reflection is fiber optic cable. Okay. So this is a fiber optic material. It's a plastic that has a high index of refraction. And so you get total internal reflection going on. Don't be mesmerized by this. This is just light escaping. Be mesmerized by inside. See how it's bouncing, totally internally reflecting. This fiber optic cable acts like a pipe for light. Okay.
It's like a super villain weapon. Like he turns it on and then like hypnotized just to do it. I mean, I'm not lying. A Marvel superhero comic.
Okay. Cool with that. It's bouncing around.
Oh my god, it is with my kids.
Okay.
Yeah, I feel like
What?
he's hiding because I like Clark Kent.
Cool with that.
He puts on his glasses, like puts on a wig, and then he's a superhero.
I don't know if you can see that. Oh.
Oh my gosh, what if he is like Luthor?
Okay. So another application. Or like fiber optic cable. That's just like big demonstration thing. So fiber optic cable, there's a bunch of the strands bundled up down here. So if you put light through here, this acts like pipes for light. Okay, good with that? So it's channeled till you get to the end, and then it escapes. That makes sense? Okay, so you can do some really cool, fun stuff. We have a lot of color. Ooh. Good with that? A more profitable application is fiber optic cable, like computer stuff. Okay, so Wintech and MetroNet are the two companies that are installing this around the county. I talked to a guy, and he gave me a piece of it. This is what fiber optic cable looks like. This is what they're putting in the orange tubes underground. Okay, this is copper wire. This is just prevents it from, or this is like a ground strip. There's two fiberglass rods that are give it strength, but the fiber optic cable is this stuff right here. And he said one of these little strands is enough to cover 10 houses of data. Okay. And the way it passes, instead of electricity going back and forth, alternating current to send data, send information, binary, just turns the lights on and off. And that's how so which do you think has less resistance? Electricity going through copper or light going through fiber optic?
I have no idea. I blocked out that year.
Less resistance, fiber optics, way less, like crazy. It's light. It's just shining light through pipes. Cool with that?
Is there actually a way to like calculate the amount of resistance in a fiber optic cable?
That was a really good question. It would be an intensity thing. It wouldn't be like a resistance thing. That gets dimmer type thing. Okay, go with that. Now, if you're the fish, remember the fish from yesterday? Okay, do that. You can do this in the swimming pool this summer. But if you're wearing a mask looking up, okay, you're seeing the girl up here. This is what you see from the girl's point of view. The sand is being totally internally reflected. It's beyond the critical angle. Okay, here's some pictures of that. So this is a hotel swimming pool. Okay, here the light's being totally internally reflected. Check this out. Here's where the banister leaves the water. Here's where you see that transition point. Higher than what it really is. Really, it's right there. You just see it right here. There's no blind spot. It's just jumping up here. Cool with that? And then these rows are from the bottom of the pool. Cool with that? Try that this summer. Cool. Got a worksheet that you know how to do all of it. That's due on Tuesday.